Welcome everyone to a session on automated theory and computability. In this session, let's solve few problems on constructing a PDA for the given context-free language. So here the first one, here the language L is made up of string W from the alphabet set ABC, and the definition of the language says A, which is replicated I number of times, is concatenated with B, which is replicated J number of times, is further concatenated with the C, replicated K number of times, and the main condition is K is equal to I plus J. Okay, so this problem has two constraints. One is all the A should occur before B and all the B should occur before C, such that the number of C should be equal to the total number of A and B. Okay, so this is the constraint that is specified in the definition of the language. Before solving the problem, let us think about the solution that can be applied. Okay, so as we all know, for the PDA to accept a string, its FSM part should be in an accepting state, and the content of the stack should be empty, right? Of course, we need to perform some push and pop operation because we need to keep track of the total number of A and B and compare it with the number of C, right? So I have to perform some equal number of push and pop operations. So what we can do is, for every occurrence of A and B, we have to push an element onto the stack, and for every occurrence of C, we have to perform a pop operation. Okay, yeah, so initially this will be the content of the stack, which is empty, and let me take an example that is valid according to the definition of the language. Okay, so let me take AA followed by B, C, C, C. Okay, so what we have two A's and a B followed by 3 C's. So total number of A and B together is 3, and I have 3 C's, right? So for every occurrence of A, so what we will do is we will push an element onto the stack. So for the first occurrence of A, I'll push X onto the stack, and for the second occurrence of A, I'll perform a push operation. So I'll get X, right? And for the occurrence of P, again I'll perform a push operation. So this will be the content of the stack after I encounter a 2A and a B, right? And for the C, what I encounter, I'll perform a pop operation, popping a topmost element of the stack, right? So if I pop the topmost X, right? So if I perform a pop on this, then I'm left with 2X on my stack, right? And for the second C, I'll again further perform a pop operation. So this will be the content of the stack after I encounter 2 C's. And for the last C, I'll again perform pop operation. So this X will be popped out and the content of the stack will be empty, right? So this is the approach what we have to follow in solving this problem. So I have performed a push operation 3 number of times, that is for the occurrence of A and B, and I had performed equal number of pop operation, right, for the occurrence of C. So the number of push and pop is equal, so hence I can say that at the end the stack will be empty. Keeping this approach, we have to solve the problem. Okay. So let us construct a PDA based on this approach. Now let's construct a PDA by considering the smallest string that is accepted by the definition of the language. So what is the smallest string that is accepted by the definition of the language? Smallest string is epsilon, because a string of length 0 will be having equal number of A, B and C, right? So here this will totally satisfy the condition where K is equal to I plus J, which happens to be 0, right? And this is how we will build the skeleton of the PDA. So I have a starting state Q node, and which should be marked as accepting, because this will accept epsilon, and let me write a stack here on the right part of the screen. Okay, so if I get epsilon, my FSM is in accepting state Q0, and the stack will remain as empty, right? So both the conditions are true, so this will be totally accepted. Okay, okay, now let us consider a string of higher length. Okay, if I take AA, BB followed by CC, CC. Okay, I have 2A followed by 2B, and which is concatenated with 4 C's. This should be valid according to the definition, right? Yeah, so Q0 upon A. So we have to push an element onto the stack. So what I will do is I'll remain in Q0 state. So upon encountering A, and if the top of the stack is epsilon, I'll push X onto the stack. So this, see, whenever I get something like this, where epsilon is written on the top of the stack element, this means I'm performing push operation no matter what is on the top of the stack, right? So when we normally perform a push operation, we are not bothered about the condition what is on the top of the stack, right? We simply push an element. So if that is the case, then we represent the top of the stack element as epsilon. Okay. So in this case, what will happen? A will be X will be pushed onto the stack for the first occurrence of A. For this A, X will be pushed onto the stack, and the same is applicable for the second A, right? So one more, I'll remain in Q0 and I'll push another X onto the stack. Okay, now when I start getting B, I should make a transition to another state, and again I'll perform push operation. I'll be pushing X onto the top of the stack. So I'll go to some Q1 state and I'll perform push operation, right? Okay, and being in Q1 state, if I encounter more B's, I'll remain in Q1. Okay, then I'll perform push. So this is for the second B encountered. Again I'll perform a push operation. So this will be the content of the stack after encountering AA, BB. Okay, now being in Q1 state, now when I start encountering C, I will go to another state, Q2, and I'll perform pop operation. So C, and if the top of the stack element is X, then I'll perform pop. So this is very clear. I am performing a pop operation on the element that is specified in as a top of the stack element, right? So this is pop, performing pop. What I am popping? I am popping X. So for the first C what I have encountered in Q1 state, I'll go to Q2 by popping X. So this will be the content of the stack after encountering C, for the C. Okay, now being in Q2 state, for the further C encountered, I have to perform pop operation. So C, if the top of the stack is X, then I'll perform pop. So what will I get? So for the second C encountered, again I'll perform a pop operation. So this will be the content of the stack after encountering two C's in being in Q2 state. Now for the third C, again I'll perform a pop operation. This third C, again I'll perform a pop operation. And finally, for the last C, we'll perform a pop operation. Yes, now we have come to the end of the string, right? So all the characters, symbols in the string is encountered, and of course the key2 should be marked as accepting state. Now in this case, I have ended up in Q2, and the stack happens to be empty, right? So both the conditions are true, are satisfied for a PDA to accept AA, BB, CC, CC, right? So this is a valid string according to the design of the PDA, right? So this will be accepted. Okay, but our solution is half done. We have to consider various other possibility with respect to strings that is valid according to the definition. So let me take an example. Okay, let me erase this. So if I take an example as BB followed by CC. So is this valid according to the definition of the language? This is totally valid because here the number of A's happens to be 0 and the number of B is 2, right? And the number of C is 2. So A plus B, the I plus J, which happens to be 2, is matching with the number of K, which is again 2, right? So this should again be accepted. So will this be accepted? Yes. So being in Q0 state, if you encounter B, you will go to Q1 state by pushing X. And for the second B, again you will push X. And for the C encountered in Q1 state, you will go to Q2 by popping X out, right? And being in Q2 state, when you encounter C, you will pop the X out. This will also, this kind of string will also be accepted by our PDA, right? Let us take one more example. What if I have string as AACC? Okay, so in this case, I will not encounter any B's and I'll have 2 A's followed by 2 C's, right? Here also the condition satisfies K is equal to I plus J, where I is equal to 2 and J is equal to 0 and K happens to be 2. So this is totally valid according to the definition of the language. So this kind of string should also be accepted, right? Okay, but Q0 upon A we have a definition, Q0 upon B also we have a definition, but we have not written what happens when we encounter C being in Q0, right? That is something what is pending, that need to be addressed, right? So Q0, okay, so Q0 upon A, I'll push X onto the stack and I'll remain in Q0, and Q0 upon another A, I'll push X and I'll remain in Q0. Now I start encountering C. So I'm done up to this point. Now when I encounter C, I don't have a definition, right? So we have to address that, and where the transition should happen, the transition should occur to directly to Q3 state, right? So I have to make a transition to Q3 state. Upon C, I have to perform pop operation and make a transition to Q2. So in this case, what will happen? I'll go to Q2 by popping X out, and now being in Q2 state, when I encounter C, I'll again perform pop operation. So this will be the content of the stack if I encounter AACC. Okay, so here there is no occurrence of B. So even this kind of problems, strings will also be accepted, right? So this is also accepted. Okay. So this is how the PDA works. Now let us consider a few examples which is not valid according to the definition, and let's see what will be the how the PDA, how the machine will address that issues. Okay. So if I take invalid string, so let me take AA BBB followed by CC. Okay, so here the number of A and B totally it will be 5 and the number of C will be 2, right? So I'll be performing 5 number of push operation and 2 pop operation. So for every A what I encounter, I'll push X onto the stack, right? So and for every B again I'll push something onto the stack. So what will be the content of the stack after encountering 2A and 3Bs? I'll be having 5 elements on the stack, right? And for the C encountered, I'll perform pop operation, okay? And for the second C, again I'll perform a pop operation, okay? So at the end, so after encountering 2 Cs, of course I have ended up in Q2, which is the accepting state, but the other condition, that is the stack is not empty, right? The stack is having some contents XXX. So this string will be totally rejected by the PD. Okay. Okay. Now what if I shuffle A's and B's? Okay. Let us check. So if I take a string BB A C C C, so what will happen here? The number of A's and B's is equal to number of C's, right? So this will satisfy one part of the constraint, that is K is equal to I plus J. But what about the order? Here B has occurred before E, right? So this kind of string should be rejected by our PD. So let us see what will happen. So when you encounter Q0, when you encounter B in Q0 state, you will push an element onto the stack. So this is the initial stack content. So when you encounter B in Q0 in the starting state, you will push X onto the stack. Okay, so this is for the first B, and for the second B, you will end up in Q1 state. You will again push a content onto the stack, X onto the stack. Now when you encounter A, so there is no definition for A in Q1 state, right? So Q1 upon A is not defined. So if that is the case, then the PDA will not move further. It will end up in some dead configuration, right? So this kind of string will be totally rejected. Okay, so our PDA pretty much works for all the, not pretty much, it works well for all the valid string, and it rejects all the invalid string. Okay, so this is how the PDA works. Okay. Now let us write the tuples value for this particular PDA. Let us see the values of all the tuples for this PDA. We start with K, which is set of all the states in the PDA, Q0, Q1 and Q2. So I have 3 states, and followed by sigma, which is the alphabet symbols used, which occurs as a part of the string. So these are A, B and C. Tau, which is the stack symbol used. We have made use of X to perform push and pop operation as an element to be pushed and popped from the stack, right? Okay, starting state is Q0, and A is a set of accepting states, which happens to be Q0 and Q2. Then finally the transition. So let us see all these transitions one by one. So being in Q0 state, when encountered A, nothing is popped, and I'll remain in Q0 by pushing X, right? Similarly, being in Q0 state, when encountered B, we'll make a transition to Q1 by not popping anything and pushing X, right? Being in Q0 state, when encountered with C, I'll pop X out. Okay, so this is the popping part. I'll go to Q2 and not push anything. Similarly, being in Q1 state, upon encountering B, I'll not pop any symbol. I'll remain in Q1 by pushing X. Q1, and when encountered with C, I'll go to Q2 state by popping X out and no symbol to be pushed, right? Being in Q2 state, when encountered with C, I'll pop X out, will remain in Q2 and no element is pushed. So these are the various transitions, set of transition for this PDA, right? Okay. So this is about solution for the problem where number of C is equal to number of A and B. So we'll solve few more problems.